In this session, we will be continuing our discussion on sensitivity analysis. So in the previous session, we performed sensitivity analysis with the help of graphical method. And we know that for our problem, we can have many number of variables, and those problems which we solve them using simplex method. So in this particular session, we will be focusing on algebraic sensitivity analysis, and we will be understanding this with respect to the simplex method. So as we know, there are two cases in the sensitivity analysis. First is the change in the right hand side, and another is the change in the right hand side means change in the right hand side of the constraint, and another one is the change in the coefficient of objective function. In order to understand this particular sensitivity analysis, let us take an example here. Suppose we have a one company called Toyco, which assembles three types of toys. One is train, another is truck, and the third one is the car. So three types of toys are there, and they are getting assembled using three operations. Now the daily limit on the available time for these operations are given as 430, 460, and 420 minutes. So if we say the daily limit, it means that it is going to be the constraint on those operations. And the revenue per unit of toy, train, truck, and the car are $3, $2, and $5 respectively. So these are the revenue. So we can understand that our objective function will be based on that. The assembly time per train at three operations are 1, 3, and 1 minutes respectively. The corresponding time per train per car are 204 and 120 minutes. So 0 minutes indicates that the operation is not used. So since we have done LP modeling earlier, we can find it out that the number of variable will be depending on the number of toys of train, truck, and car. So the variables we can write as x1, x2, x3 represents the daily number of units assembled of train, truck, and car respectively. Since the revenue per unit of these toys are given, so our objective function is maximizing the revenue. So the equation is written as maximize z equals to 3x1 plus 2x2 plus 5x1, subjected to, as we remember, the limit on the operations, that is the available time, is given to us. So 430, 460, 420 are given, and one particular toy, say train toy, it is taking 1 minute, 3 minutes, and 1 minute on these three operations. So this is the way we are going to make our constraint. So on operation 1, toy 1, toy 2, toy 3, how much time it is taking, and it is smaller than equal to 430. Similarly operation 2 and similarly operation 3. All these variables should be non-negative. Now you know that since this particular problem is a 3 variable problem, then we have to solve it using simplex method. In order to solve this simplex method, we have to convert these constraints into the equation form. So how we can convert? We are going to add a slack variable here for operation 1, slack variable in operation 2, and slack variable in operation 3. And these slack variables are x4, x5, and x6 for operation 1, 2, and 3 respectively. So without showing the simulation or iterations of the simplex method, here I'm presenting you the optimal simplex table for the given problem. So here you can see that in the optimal simplex table, x2, x3, and x6 are the basic variable, and the other three variables are the non-basic variable. The corresponding value of a z, x2, x3, and x6 are given here. Now let us change the right hand side. So here we know that we write our constraint into the equation form, and we included these slack variable x4, x5, and x6 in our constraints. So what we are going to do is we will take these slack variable on the right hand side. So if you are going to take them on right hand side, so you can see that minus x4, minus x5 and minus x6. Now, if we look this particular, say operation 1, it says that if I can reduce the 1 minute in the slack variable x4, it is actually changing the right hand side by 1 minute for operation 1. So the similar for operation 2, when we are going to reduce x5 by 1 minute, it is actually increasing the right hand side of operation 2 by 1 minute, and similarly for operation 3. So this particular thing we are going to use it later. Now this is the Z row corresponding to the optimal simplex table. So if I'm going to write an equation using this, is Z plus 4x1 plus x4 plus 2x5 plus 0 times of x6 equal to 1350. So the same equation we have written on the right hand side of this table. Let us rewrite this particular equation. So when we are going to rewrite, so this is equals to 1350 minus times of 4x1 plus 1 times of minus x4. So I will tell you why we are writing this, plus 2 times of minus x5 plus 0 minus times of x6. Now, as per our discussion in the previous slide, that if I'm going to reduce x4 by 1 minute, it is going to increase 1 minute in operation 1. So basically changing the right hand side of operation 1. Similarly, if I'm going to reduce x5 by 1 minute, it is going to increase 1 minute, going to increase the 1 minute on the right hand side of operation 2, similarly operation 3. So the same thing we have written as Z equals to 1350 minus 4x1 plus 1 time increase in the operation 1, 2 time increase in operation 2, and 0 time increase in operation 3. So this minus x4 we are writing in increase in operation 1, minus x5 we have written in increase in operation 2, and respectively for operation 3. Now this is helping me to understand that how when we are changing the right hand side of the constraint, then you know that we can find the dual price of that particular constraint. And what is the dual price? The dual price is the difference of Z new minus say Z optimal divided by the change in the right hand side of the constraint. Now look at the equation which is given at the bottom. Now you know that if suppose you are going to increase some say increase the right hand side of say operation 1, in that case the value of x1 will 0. Why? Because it is non-basic for the current problem. Second, so as we increase just one say 1 minute here for operation 1, we do not change anything for operation 2 and 3. So Z new will become 1350 plus 1 times of increase in operation 1. So if I subtract Z new minus Z optimal, so this is nothing but 1 times of increase in the operation 1. So this is giving me an idea that that this particular equation, so basically the coefficient which are given as 1, 2 and a 0, they are telling me about the dual price for the given problem. So the question comes that how we can find this. So here the equation which we have seen that the 1 minute increase in operation 1 time increases Z by $1. 2, a 1 minute increase in operation 2 increase the Z by 2, and similarly 1 minute increase in operation 3 time does not change Z. So reading this these 3 lines, we can understand that we are actually defining the dual price. Now how I can find the dual price from the optimal simplex table? So we have to remember that here we have to remember that the table should be optimal simplex table. So looking at the Z row, And we have three, in this particular problem, we have three slack variables, x4, x5, and x6. We understood its significance that the slack variable reduction of one in slack variable is actually increasing 1 minute for operation 1, similarly operation 2, and similarly operation 3. Now look at the coefficient 120. Now this 120, as we have read these three lines, these $1, $2, or 0, this is nothing but the dual price for operation 1, operation 2, and operation 3. This we can find it from these coefficient. So in a simple way, if I have to identify the dual price for each of the constraint, I will be looking at the slack variable, and this slack variable. So in the optimal simplex table, in the Z row, I will be looking at the Z coefficient of the slack variable, and I can get what will be the dual price. So the simplex method will give you directly the dual price. We don't have to calculate as we calculated with the graphical method. So the dual prices, resources for operation 1, 2, 3, slack variables are given here. Change in the optimal value of a Z are given based on the dual prices, which is $1 per minute, $2 per minute, and $0 per minute. Now, zero dual price of operation 3 means that there is no economic advantage in allocating more production time to this operation. This we can identify by looking at the slack variable value, which is nothing but which is a plus 20 in the optimal simplex table. So this means that this resource is already abundant, and that's why this particular operation 3 has a zero dual price. However, if we look at operation 1, we have a dual price of 1 and a 2. So the revenue can improve by $1 and $2 per minute. Now you remember that in graphical method, we had some questions. Now the same question, if we ask that which particular operation we should give priority. So we can, for answering this question, we will be looking at the dual price, and we know that the operation 2 has the maximum dual price among the three. Then more resources should be allocated to the operation number 2. Now let us look at the feasibility range. Now feasibility range means that you know that what should be the range in which the dual price is valid. So here we are introducing capital D1, D2, and D3. These are nothing but the changes on the right hand side of the constraint. And these D1, D2, D3 can be positive as well as negative. So here our objective function will remain the same. And here on the right hand side, we are adding D1, D2, and D3 for operation 1, 2, and 3 respectively. Now let us introduce these D1, D2, D3 in the simplex table. So here the starting simplex table is, so you know that X4, X5, X6 are the slack variable. So these are going to be the starting basic feasible solution. We have written the coefficient here. We have a right hand side, and we have just introduced D1, D2, D3, and currently they have no role. We have just included. Just see that the coefficient under X4, X5, and X6 columns that are exactly the same as D1, D2, D3. Now we are going to follow the simplex method, and let us identify the optimal simplex table here. So the optimal simplex table, as we know, X2, X3, and X6 are basic solution. Corresponding coefficients are written. Their solutions are written. Now look at the columns of X4, X5, X6, as well as D1, D2, and D3. You can see there is a similarity. Why? Because we started with the identity matrix. Here also it was identity matrix, and after following the same operation, so we get the same coefficient. Now in this case, we don't have to introduce these D1, D2, D3. What I can do is I can solve the original problem as it is. So this is the table, and I can introduce D1, D2, D3 at the last. I'm repeating again. We are solving the method, we are solving the LP model as it is by the simplex method. Once we get the optimal simplex table, now let us introduce D1, D2 and D3. So here D1 for constraint 1, so that's why it is above X4. D2 for constraint 2, that's why it is above X5. And D3 is above X6, that's why it is above. How I can find the equation which are given below? So let me go back here. Now when we have this right hand side, if I want to write Z, Z is equals to 1350 plus D1 plus 2D2 plus 0. Similarly, X2 I can write as 100 half D1 minus 1 by 4 D2 and this. So the same equations I have written there. So our objective is now, since we are not introducing D1, D2, D3, can I get the same equation? Yes. So we have included this D1, D2 and D3. How we can get it? That let Z is equals to 1350 plus 1 by 2 D1 minus 1 by 4 D2 plus 0 D3. This is exactly the same equation. For X3 variable, we get now for there was a mistake. Let us take Z row first. Z row is 1350 plus D1 plus 2D2 plus 0 D3. Now let us take X2 variable. So it is equals to 100 plus half D1 minus 1 by 4 D2 plus 0 D3. So we are going to get the same equation. I hope you remember that when we have learned the simplex method for the first time, I told you that the last column which was corresponding to the right hand side or the solution, those are nothing but the values of Z, X2, X3 and X6. Now with this, we are going to find the feasibility range for the dual prices. Now the feasibility means that since we are changing the right hand side, the value of X2, X3 and X6 can change. This we can understand. Now we have to see that X2, X3 and X6. So these are basic variables. So these basic variables should be greater than equals to 0. And in that case, what should be the value of a D1 and a D2? So this D1 and a D2 are giving me the range of the dual price so that X2, X3 and X6 will remain feasible. So let us modify the right hand side. So the operation 1, we have modified say 480, operation 2 and operation 3 also modified. So accordingly, I can find D1. How? 480, that is the change, minus what was the original 430. So we get 50. Similarly, D2 is minus 20 and D3 is minus 10. If I'm going to include in our equations, so the condition is feasible, feasible, and the last one is minus 110, which is smaller than 0. So it is infeasible. So we know that this particular change is not acceptable. Let us take another example where we have D1, D2, D3. We are including into this equation. And we can see that X2, X3 and X4, all of them are greater than 0. So this is the feasible range. Now, if I go back to the previous slide here, in this case, you remember that we have written the condition of X2, X3 and X4 in terms of D1 and a D2. Have you thought about why we are not writing the equation for other variables? We are not writing those equations because other variables are non-basic and they will always 0. So that's why we are not introducing D1, D2, D3 with them. Right. Now, once we have identified, yes, these are feasible solution. Now question is, can I find what is the objective function? So the objective function I can find by using Z is equals to 1350 plus D1 plus 2 D2. So this equation we have already written, or I can write the original objective function as 3x1 plus 2x2 plus 5x3. I can use any one of them. So by including it, I should get a value of a Z 1296. Now there are two observations in this slide. First observation is, we know that when we are going to change the right hand side of the constraint, our solution will change. Now we have looked X2, X3 and X6 with the help of these equations. we found the value, the change in the value or the new value of x2, x3 and x6 as 88, 224 and 78. So here you can see that by introducing capital D1, D2, D3, we can find the new value of x2, x3 and x6 without resolving this problem with the new right hand side. So the right hand side has been changed based on D1, D2, D3. We are not solving the problem again. What we did it, we use the equation and we find what are their values. So first observation. Second is, if I have to calculate Z, I have two equations. I can use any one of them and get the value of a Z. So you can see that in a straightforward manner, we are getting the values of basic variables and we are getting the value of a Z, that is the new Z value. Now here we are presenting three cases. Three cases means that let we change the right hand side of constraint 1, but the constraint 2 and constraint 3 remains the same. There is no change. So can I find the range of D1? So in this case, since D2 and D3 are 0, I have included those condition into x2, x3 and x6 equation. Now these equation, if you simplify, it says that D1 is lying between minus 210. Same observation I can do when we are changing only operation 2 right hand side, but operation 1 and operation 4 remain the same. So in this case, D1 and D3 are 0 and we can find the condition by putting the value, basically the condition in x2, x3, x6 equation, and we can say that D2 is lying between minus 220 to 400. Same thing we can do when we assume that there is a change in the right hand side of operation 3, but no change in operation 1 and a 2. So this will give me the range for D3. Important point to understand that the ranges of D1, D2 and D3 are valid for these cases only. So here we are assuming D2, D3 are 0. In second case, we are assuming D1 and D3 are 0. And similarly for the third case. So these cases we have written, as well as we have also written the operation 1, 2, 3, their respective dual price, their respective feasible condition, the minimum, current and the maximum values we have written here. Now, there is a one important observation. Suppose we are going to change D1, D2, D3 simultaneously. Now, if I'm going to change, now look at D1 value. It is not lying in the range. Look at the D2 value. Yes. Look at the D3 value. Yes. So when I'm changing, D1 is not lying. But when I'm putting these D1, D2, D3 value, you can see X2, X3, X4 value, all of them are feasible and there is Z value we can calculate. So as I said, these feasible ranges are valid. So for operation 1, this is valid when there is no change in operation 2 and 3. Similarly this. But when we are doing simultaneous change, we have to put these values in the equation of X2, X3 and X6. Then only we can check the feasibility. If they are feasible, we are going to accept the value of D1, D2, D3, and we can calculate the new value of Z. So what we have understood from this sensitivity analysis with respect to the change in the right hand side, that the dual prices remain valid so long as the changes in DI in the right hand side of the constraint satisfied all feasibility condition when the changes are simultaneously or fall within the feasibility ranges when the changes are made individually. So we have to put the value of D1, D2, D3, check the feasibility as we have shown in the previous slide. If all are feasible, then dual price remains the same. For other situation, as we know that if we are going to get a solution, we don't get the feasible solution, then we know that either we are going to resolve the problem or we are going to use post-optimality analysis. This post-optimality analysis I will be discussing in the next chapter. Now, in the previous slide, we discussed about the change in the right hand side of the constraint. Now, we will be focusing on objective function, basically change in the coefficient of the objective function. In order to understand that, I'm introducing one conceptual term that is called reduced cost. So let us understand what is that. So this optimal value of this Z equation at the optimal from the optimal simplex table. So this is shown at the bottom. So we remember that we can write this Z equation in terms of Z plus 4x1 plus x4 plus 2x5 equal to 1350. We are taking all the variables on the right hand side. Now let us look into it. The optimal value says that x1 is 0. So we remember that x1 was non-basic variable. If it is going to take a positive value, so we know that we are going to subtract -4. So this means the Z will reduce by $4. So X1 can be think of a unit cost as it reduces revenue. So it comes. So therefore, what we can think here is now let us take an example of a mobile phone. Now, when we are making a mobile phone, we need many resources. Resources includes, say, screen, its circuit, its software. It also includes the operators which are working and finally giving me a mobile phone. Now, if I have this mobile phone, I can see how much money I am investing into it. And so that will be the unit cost of the product. Now, when I'm going to sell, so this is the revenue I'm going to get it. And you know that when the revenue is less than the unit cost, I'm not going to get a profit. And this is exactly same thing happened with X1, that the revenue is less as compared to the cost, as compared to the unit cost. So how we can introduce reduced cost? So the reduced cost is the cost of consumed resources by 1 unit minus revenue. So the resources which are used to make a one mobile phone minus the revenue per mobile phone, that will give me the reduced cost for this particular unit. So this reduced cost concept, we are going to use it now. Now here is can we make X1 profitable? Because currently it is unprofitable. There are two ways. I can increase the unit price. So unit price means this is market driven, so I cannot change it. Or I can decrease the unit cost of the consumed resources, that we can do it. So here we have two options. Either I can increase the price of the cost of the mobile phone so that I should get some profit, or I can, rather than I use very good quality of a material to make a mobile phone, let me use some standard material so that the unit cost can reduce. Now for condition, so you remember that when we had when we change the coefficient of the objective function, our condition was that when we are going to change the coefficient, the objective function coefficient, our optimal solution remain unchanged, means remains the same. So this particular statement has a meaning. Now you remember that in the simplex method, we get the optimal simplex method when there is no entering non-basic variable. Now we are solving a maximization problem. So maximization problem means I will be looking for the most negative coefficient in the Z row. If there is no most negative coefficient for maximization problem, this means I should stop, and this is the optimal simplex table. Now this concept, we are going to use it later. So I have defined here, so we will remember it. Now in TOEIC model, we have small d1, small d2 and small d3 as change in the unit revenue of toy, truck, train and the car. So this representation we will remember now. So the starting simplex table. Now if you are going to write a starting simplex table for the original problem with the change in the objective function, so you know that only the Z row will change, but the other rows corresponding to the slack variable x4, x5 and x6, that will remain the same. So that's why I'm showing you only the Z row here. When we are going to follow the similar Gauss-Jordan operation and other simplex method, we are going to get this simplex table. This is the optimal simplex table. Now, I'm coming to the previous discussion. We remember that for maximization problem, the optimal simplex table is achieved when there is no entering non-basic variable. This means that the coefficient of a z of all non-basic variable is either 0 or positive value. Now, in this, when we are changing the coefficient of objective function, we want that our optimal solution will not change. How it can happen? It can only happen when there is no entering variable yet after changing the coefficient of the objective function. I'm repeating again. The optimal solution will remain the same for the change in the objective function coefficient when when there is no entering non-basic variable. So if I look at the optimal simplex table, we know that the first non-basic variable is x1, which is written in terms of d1, d2, and d3. Similarly, another non-basic variable is x4, and another non-basic variable is x5. So as per our discussion, x1 it cannot enter into the basic if the value is 0 or greater than 0. Same thing for x4 and same thing for x5. So this particular condition we are going to use in the next slide. So here the table is the same as the last optimal simplex table except the z equation. The change in the z equation coefficient can affect the optimality of the problem only, and that is what we discussed in the previous slide. It means that there is no need to perform simplex steps for the reduced cost, but because I can find the reduced cost from the simplex table directly. Now I'm introducing the reduced cost. Now reduced cost is the unit cost minus revenue. Now you remember that for a maximization problem, if the non-basic variable z coefficient is negative, this is going to enter into the table, meaning that the reduced cost should be smaller than 0. If it is greater than 0 or equal to 0, then it is not going to enter into the table. So here you look at the equation of a z coefficient of x1. So now our objective is, can I find this particular form of a z coefficient for non-basic variable x1, x4, and x6 from the optimal simplex table? So the answer is yes. How? So you remember that we included d1, that is the change in the coefficient for x1 variable, similarly d2 for x2 and d3 for x3. And we know x4, x5, x6 has no contribution, so the change is 0. This is the optimal simplex table. Now the z, we are on the right hand side, we are introducing, so we are adding this new particular row on the top. Now let us look at the yellow part. Now we are adding one more column. What is that? For z, it is always 1. For x2, what is the change? D2. What is the change for x3? D3. And what is the change of x6? It is 0. So these are the changes in the objective coefficient. Let me show you. So these are the changes in the objective function coefficient. Now, can I use this particular form of the simplex table, and can I find the optimality range by looking at the condition? Now, let us take x1 variable. So I'm writing the left hand column as 1, d2, d3, 0. This is the same. And we have x1 column. So these are the coefficient of the optimal simplex table for corresponding to x1. We are writing d1 because it was the change in the coefficient of x1. And we are writing x1 column into the left hand. So 4 into 1, d2 into minus 1 by 4, d3 into 3 by 2, 0 into 2. So I have written it. So what is the reduced cost? Reduced cost is how much we have consumed. We have consumed 4 minus 1 by 4 D2 plus 3 by D3 minus what is the revenue? We are going to get a revenue of D1, and this is the reduced cost of X1. Apply the same rule for the solution Z. So instead of this, I can have a Z column and I can find the same thing as I will show you that here if I'm going to find this Z, so we have this left hand side, we have this right hand side, and I can find 1350 plus 100 D2 and 230 D3. So this is what I get it. Now the current optimal solution remains optimal when the new reduced cost is non-negative for all non-basic variable. And that is what we discussed earlier. So if it is going to be non-negative, either it can be 0 or it can be positive. So you know that X1 variable cannot enter into the table. So it will never be the entering non-basic variable. And this is the condition of optimality for a maximization problem. Since we want our optimal solution should not change, so we want the reduced cost of X1 should be greater than and equals to 0. So we have three non-basic variable. We have written the condition. So can you see the form? 4 minus 1 by 4 D2 plus 3 by 2 D3 minus D1 greater than 0. So this condition, you know that this reduced cost should be greater than 0. So this non-basic variable will remain non-basic for the given problem. Let me go back. Now you remember that what was the coefficient of X1 under Z? It is 4 minus 1 by 4 D2 plus 3 by 2 D3 minus D1. This is exactly we get it here. So now we will remove this X1 column, put X4 column and then X5 column. We get three different equations, and the condition that the reduced cost of non-basic variable should be greater than and equals to 0 for maximization problem. How about the basic variable? So should we look into it? Now you remember that we discussed this thing earlier, that in the simplex table, the Z coefficient of all basic variable are 0. This means the reduced cost of all basic variable always be 0, so that we will remember. So we are not worried about the basic solution because their reduced cost is 0. Now let us make the changes. Here we have the objective function. This objective function, original objective function, is changed to the another form. Looking at these two objective function, we can find D1 is 2 minus 3 minus 1. Similarly, D2 and D3. I can put these values in this. I can find that first equation 6.75 greater than 0, yes. Second 0.5 greater than 0, yes. 2.75 greater than 0, yes. So all three conditions are satisfied, meaning that if we are going to change the coefficient of objective function, so the optimal solution will remain the same as per these conditions. So for this, X1 remain 0, X2 100, X3 is 230 and Z is 1480. Now here only the solution is changing. This is, you have to understand it. X1, X2, X3, these values that remains the same. I can show you the optimal simplex table. So the optimal simplex table, X2 is 100, X3 is 230 and X1 is non-basic, so it is 0. So here the solution remains the same, but the Z value will change. Why? Because you look the Z function here. Since the coefficient have been changed, I put the value of X1, X2 and X3 here. I can get the new Z value. Now, important point we have to remember that for minimization problem, the reduced cost should be smaller than or equal to 0 to maintain optimality. Again, let us find some cases here. Case 1 is we are changing one dj at a time. So we are putting D2 and D3 0. Let us find the range of D1 because we have these three equations with us. So we can say that D1 will be lying from minus infinity to 4. Similarly, D1 and a D3 is 0 for case 2. I can find the range of a D2, and D1 and a D2 is 0. So I can find the range of D3. Again, it is important to note that this particular range is valid when D2 and D3 are 0. Similarly, this range is valid when D1 and D2 are 0. And this range is valid when D1 and D2 are 0. Here, you have to understand that if I'm finding this particular range, say case 1, this says that if D1 is lying between this, our optimum solution will remain the same, meaning the value of x1, x2, x3 will remain the same. Similarly for case 2 and case 3. Now, unit revenue of a toy truck. Now I'm coming back to the previous question that can we make our x1 variable profitable? So that we are going to solve it in the next slide. So let us take unit revenue of a toy truck. So it is 2 plus minus 2 smaller than equals to 2 plus D2, which is smaller than 8. So basically unit revenue. So what we are finding is, since we have identified the range, say this is for D2. So I'm including the original value. So you remember that the original coefficient of a D2 of X2 was 2. So we have just added. So the unit revenue of the toy truck, if it is lying between 0 to 100, then the optimum solution will remain the same. Now, can we change the simultaneous changes in the D1, D2 and a D3? So if we do simultaneous change in D1, D2 and D3, you can see that the first condition is minus 3.5 not satisfied, second is satisfied, third is not satisfied, meaning that this is we are not going to use it because it will change our optimal solution. So at the end, the optimal values of the variables remain unchanged so long as the changes in the small dj in the objective coefficient satisfy all the optimality conditions when the changes are simultaneous or fall within the optimality range when the change is made individual. So the suggestion is you put the value of D1, D2, D3, the changes into the equations and make sure that the condition is satisfied. And also note that when you are solving a maximization or minimization, the condition will change. For other situation, when the simultaneous optimality conditions are not satisfied or the individual feasibility ranges are violated. So basically the resources is to either we are going to resolve the problem or we are going to use post optimality analysis, which we will discuss in the next class. So here with this, I'm concluding the chapter on simplex method, followed by the special cases in LP. Then we discuss the sensitivity analysis with respect to using the graphical method. And then we discuss the sensitivity analysis with respect to the we are using the simplex method. Now here, if you see, when we are doing the sensitivity analysis with using the simplex method, when we are changing the right hand side, we want to know what is the value of capital D1, capital D2, capital D3, so that this the solution, the basic solution will remain feasible. So that is going to give me the range, and in that particular range, our dual price will remain the same. So that is what we did it in the sensitivity analysis. If we look at the objective function coefficient, we want to change it in such a way that our optimum solution means value of x1, x2, x3 should not change. So we did it with the help of a small d1, a small d2, small d3, and then we are putting a condition. The changes in a small d1, d2, d3 we put into the condition and check whether the optimality condition is satisfied or not. So with this, I am concluding this session.